Okay, so this is joint work with Arnav Ganguly, and it's already on archive. In this paper, I think there are three probabilistic results that are so two of them are, I think, more interesting from a math bio perspective, and two from a statistical perspective. So I'll focus on only one of the I think results that I think is interesting from both math bio and statistical perspective. So, which is the interacting particle systems formulation. So I'll start with this quote by Wolfenden and Schneider about multiscale reactions and how different the reaction rates could be. And so it says that the fastest known reactions include reactions catalyzed by enzymes. But the rate enhancements that enzymes produce had not been fully appreciated until recently. So when you don't have enzymes, some of these reactions could be among the slowest that has ever been measured, and with half times approaching the age of Earth. So you can see that enzymes, when you have, they are really, really fast. Now, when you have a multi-scale system like that, and my prototypical example would be a Michaelis Menten type enzyme kinetic reaction, you are inherently not observing some of the reactions that are fast. So you will potentially observe only the slow reactions. Then a question from a statistical perspective is, how do you then estimate parameters of such a system when you don't observe the system? So that's the main question that I would like to answer through the example of a Michaelis Menten enzyme kinetic. So I'll describe the standard Michaelis Menten enzyme kinetic reaction. So I was told that, so not everyone might be familiar with these type of, so I'll pick the simplest version of the Michaelis Menten enzyme kinetic reaction. In the paper, we have multiple intermediate species, and we explain how to do the same thing for the more general model, but here I'll talk about that. Then I will talk about the mimicking interacting particle system, and then I'll talk about how we can do parameter inference using the mimicking particle system using ideas of propagation of chaos. So in the simplest form of the Michaelis Menten enzyme kinetic reaction is that you have an enzyme, which I'm going to denote by E, and you have a substrate. So this one molecule of enzyme and one molecule of substrate, they can combine together to form one molecule of enzyme substrate complex. So this is the binding reaction, but this could also unbind, meaning that they combine, but they unbind, which is the reverse reaction. The other reaction is, so if the enzyme substrate complex then could create a product, typically a protein, and then the enzyme is then freed up. So you can view the enzyme as a server, if you come from a queuing theoretic background. In the deterministic world, what you would do is write down ordinary differential equations to describe the evolution of their concentrations. So if I follow a mass action kinetic, then the ordinary differential equations are very easy to write down, and they will look like this. So we get, following mass action, we get this term and this term. So now there are two conservation laws here. So one of the conservation laws is that the total number of enzymes that you have, that's conserved throughout. So each enzyme molecule is either in the free state or in the combined state. So if they are servers, then they're either busy when they are combined with an S molecule, or they're free. And then the total number of, let's say, initial substrate molecules, that's also conserved. Now, the good thing, or the interesting feature of such reactions, is that if you simulate or if you solve the system of ordinary differential equations, then you see that the species C, the complex, reaches a steady state very, very quickly, while the other species remain transient. So the species C reaches, let's say, a quasi-steady-state very quickly. And this is not just from the numerical solution of the ODEs, but empirical data also suggests that. So this then led us to what we call the quasi-steady-state approximation, or the standard quasi-steady-state approximation. The way you would do it is you would then say, okay, because the species C reaches a steady state very quickly, so I'm going to set the time derivative of C to 0 and use the conservation law, and that would give me a steady state value for C. And I can plug that in the other equation, and this will give me a single equation for S in terms of the quasi-steady state values. So this is what I want you to focus at the moment. So what I've done here, you have 3 different reactions. You can view this quasi-steady-state approximation as an approximation from the system consisting of, sorry, S plus E going to C, going to E plus P. This is an approximation to a system that looks exactly like this. So this is approximately equal to that. And in which case you get a single equation, which I'm going to call dsdt to be minus h theta of S. Now, there are a number of parameters in this system. So kappa 1 here and kappa 2 and kappa minus 1. But from this set of equation, I think the key parameter that biologists are often interested in is this parameter, which is called the Michaelis Menten constant, which is the ratio of kappa minus 1 and kappa p, or I think I denoted maybe kappa 2 sometimes, divided by kappa 1. So we have these two parameters. And now we can think of this as just a dynamical system. And you might be wondering, okay, how do I estimate the parameters of this system? Just to give you some context about how vastly these types of approximations are used in and not just in the literature, but also like in the industry. So there is a huge amount of literature on its validity, use, and mass abuse, because it has been shown that this approximation is not valid under certain circumstances, and yet people continue to use it, and many extensions of this type of approximations have been proposed in the literature. So from the deterministic world, you can find good resources from Santiago Schnell, Jae Kyung Kim, Jaffaridi. On the stochastic world, Tom Kerr, Seiwan, they're experts on deriving such multiscale approximations. Now, as I just said, the standard quasi-steady-state approximation, at least heuristically, this basically amounts to approximating this set of equations by just a single equation that looks like this, where you no longer have mass action, but you have a non-mass action type propensity function, which in this case is very easy to derive. And in other cases, it might not be easy, but there are methods both in the deterministic world as well as in the stochastic world to derive this thing. So if I go back to the question that I started with, so if I have a multiscale system, I don't observe all reactions, then how do I learn such a system? Well, then you might say that, okay, if I do a quasi-steady-state approximation, that reduces to a single reaction. If I can observe just this reaction, then I can just try and learn this equation. I don't need to worry about the other things. So it seems like the issue of unobserved reactions is basically solved if you can do stochastic averaging or quasi-steady-state approximation. And this is partially true. So we still need to worry about what do we mean when we say we observe this reaction? Do we mean we observe this reaction completely or partially? So there will be still challenges, but at least it seems like if we can observe S going to P in some sense, then we have a chance of learning the system. Okay, so now I want to tell you how we can learn such a system when we operate in a regime that I call the extreme sparse regime, where you don't observe the state of the system at all, but you only observe a small number of time points when P molecules are created. And this methodology is quite general, so it could be. I will explain it in the context of Michaelis Menten, but you can think of it being applied to many different contexts. So a question to the mathematical biologists here. So what other system we can reduce to a single equation like this? Now, I mean, if we were doing the talk in person, then I would probably just go and ask people, but I'd maybe just give an example. So think of the standard SIR model. Oh, there's something in the chat. Yes, epidemiological model, exactly. So if I have an SIR model, you can start with an ordinary differential equations, and you can write, so you have ds dt, you have di dt, and you have dr dt, but you can reduce them into a single equation. In fact, it doesn't need to have a single infected compartment. Even if you have multiple compartments, you can still do it. And yes, also many ecological models. That's right. So there are many different models which are reducible to this form. So which means that the methodology that I'm going to talk about will be applicable, modulo some assumptions being verified. Now, a question to our statisticians. So how do we learn such a system? Let's say you have access to a good amount of data. I would say the most straightforward would say, okay, I can just do least squares estimates. So I have data, I solve the ODE, do a least square fitting, and then I'm done. Or if I don't believe the ordinary differential equation is a good representation of a continuous time Markov chain model, then I can still do Gillespie likelihood function, Doob Gillespie's likelihood function, and then that would also work. Maximum likelihood, yes, many different ways. But all of these methods somehow require you to observe S, and S in the deterministic world is the concentration. If you are talking about, which is concentration, sorry, it's working very slowly, so it's not picking on this. Or the number of molecules, right, which I'm going to call population counts. So either way, both are functions of your population counts. So if you don't observe your population count, then how do you learn such a system? And I'm not talking about not observing at all times, but at all. So if you don't observe your population times at all, but let's say you have access to a random sample of product formation times. So I have this reaction, and I don't observe the population size of S, either in the form of concentration or count at all, but I only know some time points when some molecules of P were produced, observed up to some time point. So how do you then learn such a system? And your T1, T2, they could also be truncated and censored. For instance, I don't even have these values exactly, but I only know that they belong to certain intervals, or all of these things. So this is what I call the extreme sparse regime, because if we have data like this, or just an example like this, then you cannot actually reconstruct the system state. Which means the traditional methods, if you want to do maximum likelihood or least squares, or if you have even, let's say, some MCMC regime, they are not at least easy to work with, and I do not think they will actually work if you have such a small amount of data. and here's the main message or the claim. So my claim is that if your data is just these time points, T1, T2, some Tk, and here I'm assuming that these are exact values, not the truncated or censored ones, but even if they are, you'll get a similar expression here. What you do is you solve your ordinary differential equation at those time points, take the negative derivative of the solution, and you just do a product. And that is an asymptotically exact likelihood function. So this is what you can take as your objective function, and then you can do your maximum likelihood estimator, or you can go Bayesian. You can put some prior on your parameters and do estimates. And so there's a question: how big is T? T is any fixed number. It doesn't have to be big. So we are not assuming that even neither K is big nor T is big. So this is asymptotically exact as long as the population size is the underlying population size is large, which means as long as the ODE approximation is large. Okay, so there's a great. Okay, so the prefactor drops out of the maximization. No, it doesn't, because S, the solution of your ODE, depends on the parameters. So yes, so this is an important quantity. So you do this product, but you have to keep the prefactor itself, because the solution. So I should maybe write S theta of T everywhere. So the solution of the ODE depends on theta. Okay. And again, this works not just for the Michaelis Menten reaction, but also SIR, SEIR, mass action, also on random graphs, like configuration model random graphs. So we have some joint work with Greg Rampala. Also, when you have multiple diseases, which is joint work with my PhD student, Dan Harborn and John King. So, and I suppose, as Leah pointed out, maybe some ecological models as well. So this is the main claim. And now I'll try and explain why this is an exact likelihood function and why this should work. So that's the main part. Okay, the idea is to use propagation of chaos, which means that I need to work with an interacting particle system, which means that from the population level, I need to go to the individual level. So that's what I will do. So the idea is that if I have been given this reduced model, either through stochastic averaging. So in the paper, we give an example of how to do the stochastic averaging when you have multiple intermediate species. But let's say somebody has given me the stochastic averaging, or I believe that this is reducible like this. And we will assume that the function h is Lipschitz. Now, consider a particle system of n substrate molecules, so which I'm going to denote by S1, S2, up to Sn. And consider n different reactions. So this is for I going from 1, 2, up to n. Yeah, this writing device is not very reliable, but okay. And what I'm going to do is, now here's the interacting particle system. Consider n stochastic processes, and the behavior of which will depend on n. So yi n of t is 1 if the ith substrate molecule has not undergone a conversion into p molecule by time t. So it starts at 1, stays at 1 for a while, and as soon as this reaction, the ith reaction has fired, it converts to 0. So it's an extremely simple interacting particle system. And also keep track of the average. So the average of these stochastic processes. Now, when the number of particles is very large, or intuitively we feel this average should be very close to the deterministic limit, the ODEs. Okay. But we need to define the propensities for these reactions. So you see, I have defined just there are n reactions. How do we define the propensities for these reactions? We want in the limit this average to converge to ds d theta to be minus h theta of s. But how do we then define? It is very tempting to think that h theta should be the right propensity, but that's actually not good enough. So we'll have to do some work to get it right. If I just try and apply a functional law of large numbers, this suggests that the macro level propensity should be something like this. So at the from a continuous time Markov chain perspective, but if I then think of the individual level propensity or per molecule propensity or instantaneous pressure on any specific ith reaction, then what we have to do is we take h theta of the average divided by the average. So this is what is the right per molecule propensity, or the propensity for the reaction Si for the ith reaction is going to be. So now we can describe the dynamics very easily. So it's a very simple stochastic process. It starts at 1, and then at some point it goes to 0. So it starts at 1, and then I have a Poisson random measure. And as I said, this g theta, which is just h divided by y, the per molecule intensity, this is multiplied by this y. So when this is 1, it exerts this instantaneous pressure, and then whenever it jumps, so there is a jump in the Poisson random measure, then it turns to 0, and then it just stays there forever. So that's the interacting particle system. Now, the main idea or the motivation for me was to not have to keep track of the population size. So we wanted to look at our data was supposed to be just some individual transfer times. So what I'm going to do, I'm going to create, look at these transfer times, so what I'm calling tau I of n. So this is the time of conversion of the ith particle from S to P. Okay, so this is a stopping time for the ith species. And you can show that as n goes to 0, it goes to infinity, then the average, population average, does indeed converge to the ordinary differential equation that we started with. And not only that, if we start, so this already means that when n is large, the behavior of the interacting particle system should be approximately equal to the behavior of the original continuous time Markov chain model that we had, and the individual transfer times of the original model should be also very close to the transfer times that I observe in this in the interacting particle system. So, in order to formalize, let's say, a likelihood function for these transfer times, now here's a crucial, I think, step to understand. So, if I take the solution of this ODE, now this solution determines a probability measure on 0 to infinity, which is exactly so on any interval 0 to t, you take 1 minus the solution. So if you write it explicitly, it's 1 minus e to the power this, and there is a tiny amount of mass, not necessarily tiny, it depends on the function, but there is a mass at infinity. So it's a probability measure that will not have a finite mean, but it's indeed a probability measure. And let us write by capital Phi the joint probability law of, so let's say I fix m indices, so m particles, and I look at their transfer times, and I look at the joint distribution of these transfer times. Okay, so it's not so easy to write down in this case because of the interactions, but it's a weakly interacting particle system. So in the limit, we expect that the effect of they will be independent. So that's what we want to establish now. So we started with this interacting particle system, which is mimicking the original chemical reaction network. Now let us consider another fake interacting particle system, but this interacting particle system is even more trivial. So it's completely IID. So I have, let's say, IID Poisson random measures and IID stochastic processes, YIs, that start at 1 and they turn to 0 after an amount of time. And the intensity I have now replaced. So in the original interacting particle system, it depended on the population average. I have replaced the population average by its deterministic limit. So this is now completely IID. And for this system, when I look at the transfer time, its probability law is very easy to calculate because it's just probability that there is no transfer by time t is the same as the stochastic process remains 1 till time t, and it is just by construction 1 minus capital phi of t, the probability measure that is induced by the dynamical system. And you can actually prove that if I look at any finite collection of particles in the original interacting particle system, they will say if m is fixed, as n increases, they will converge to y1, y2 up to yn in L1 as n goes to infinity. So there is in the limit, y1, y2, ym, we know that they're independent. So what this basically means that they will converge the original chosen m particles, even though they are dependent in the limit, they will be independent in L1 sense. And not only that, because of this L1 convergence, then you know that their corresponding transfer times, which is stopping times, they also converge weakly to the corresponding stopping times of tau1, tau2 up to tau1. But this is good enough for us because this already means then I can just, so what is the limiting likelihood function? So this limiting likelihood function is exactly the law given by the law of the tau1, tau2, tau-m, but tau1, tau2, tau-m by construction is just given by the ordinary differential equation. So we get a likelihood function that looks like this. So which basically gives a justification to the claim that I started with. Now, just a small example. So for instance, if I take the Michaelis Menten enzyme kinetic reaction, there are two parameters, as I said, the Michaelis Menten constant, which is shown on the right side here, and the rate of product creation. If I just maximize this likelihood function, so here, I don't remember what is the size of the total population, I think maybe 10,000 or so, but I'm looking at a tiny little fraction of conversion times. And so I think it was 500 or something like that. So I take 500 and that gives me 1 MLE estimate. And then again, I take a random sample of 500 transfer times, that gives me another one. And then I create these histograms. As you see that this is fairly accurate. If you want to go Bayesian or semi-Bayesian, or if you want to use Hamiltonian Monte Carlo, which I have tested, this works equally well. Or yeah, so this works very good. So I think I'm close to the end of my time. So just to conclude, the main idea here is that there are a lot of chemical reaction networks that could be reduced to a single reaction that looks like a transfer from one state to another. For instance, Michaelis Menten, but epidemiological models as well. For those kind of models, you can get the right propensity function by means of stochastic averaging, which I haven't talked about here, but in the paper, we give an example. And you can apply this interacting particle systems-based approach to construct a likelihood function, and which seems to be, which is fairly accurate. What remains to be proven is the consistency and asymptotic normality of such estimators. So for instance, do maximum likelihood estimators, it should be, it doesn't appear to be too difficult for the Michaelis Menten case using a continuous mapping theorem or a version of continuous mapping theorem. But for general chemical reactions, it's still work in progress. So maybe next time I can report on that. So with that, I would like to thank you for your attention, and I'm happy to take your questions.